The Webb can see so far away that it picks up light that has been moving for over 13 billion years. However, the light has been stretching for the farthest galaxies because the universe has been expanding. We are almost back in time to the Big Bang. It may look like the universe is endless, but everything in it came from something called the singularity. At this point, this is what we know about the Big Bang theory. But the James Webb Space Telescope, JWST, has shown us amazing new things about how the world began and how it has changed over time. A famous physicist named Brian Cox has said that the amazing things the JWST has found could change how we think about the whole world. Come with us as we explore these new discoveries from space that have the potential to change the way we think about things. The James Webb Space Telescope is a great thing for studying the universe. It was named after the famous NASA chief James E. Webb. This telescope is a big step forward in technology compared to its predecessor, the Hubble Space Telescope. NASA, the European Space Agency, and the Canadian Space Agency worked together to make it. The JWST is better than its predecessor because it uses cutting-edge technology and a design that makes it possible to study the universe in more detail than ever before. The JWST, on the other hand, takes pictures of faraway celestial bodies that are clear and sharp because it mostly works in the infrared range. Because of this one-of-a-kind feature, it can see through cosmic dust and catch stellar objects that we couldn't see before. The JWST's main mirror is 18 hexagonal segments long and 6.5 meters wide, making it much bigger than the Hubble's. At the second Lagrange point, L2, which is about 1.5 million kilometers from Earth, it orbits the Sun in sync with Earth. This gives us a stable, uninterrupted view of the world. Looking into the farthest reaches of the universe requires not only traveling through light years, but also going back in time. The JWST uses infrared tools to look at things in space and events that happened billions of years ago. Because the universe is expanding, the light these things give off is redshifted, going from being in the visible spectrum to being in the infrared spectrum or longer. Luckily, the JWST can pick up infrared light from very far away celestial bodies. This lets scientists study how stars are born, how galaxies form, and how atmospheres of exoplanets work. Its most recent important finding is that it has found an unimaginable number of galaxies at the edge of the universe that can be seen. This finding calls into question the truth of the Big Bang theory, which makes us rethink our basic ideas about the universe. Let's take a quick look back at the past of space exploration to get a better sense of how we got here. By observing celestial bodies, early civilizations like the Greeks and Chinese set the stage for knowing how planets move. Newton's laws, written in the 1600s, gave us a way to think about spaceflight. Edwin Hubble was a famous and important astronomer who made important breakthroughs in cosmology and observational astronomy at the beginning of the 20th century. His studies showed that faraway nebulae were actually separate galaxies a long way beyond the Milky Way. This changed how we think about the size and scope of the universe. Hubble's law, which he came up with, said that galaxies farther away were moving away faster, which showed that the universe was expanding. The space race began after World War II, with Sputnik from the Soviet Union being the first man-made satellite to reach orbit in 1957. Other important events included Yuri Gagarin's flight into orbit in 1961 and Apollo 11's landing on the Moon in 1969. In 1990, the Hubble Space Telescope was launched, giving us a view of the world that was clearer than ever before and more amazing than we could have imagined. The history of observations in the past to the modern marvels of the James Webb Space Telescope shows how our knowledge of the universe is always changing. It showed how big space really is and changed some important ideas in astronomy. Let's look at the Hubble Space Telescope, HST. It took the famous Pillars of Creation picture in the Eagle Nebula, which showed a star nursery made of huge stacks of gas and dust. It was also impressive that the Hubble Deep Field was able to find thousands of galaxies in what looked like a blank area of space. The HST also looked into the atmospheres of other planets and found elements like water and organic chemicals on faraway worlds. This suggests that there may be places outside of our solar system where life could exist. It showed how huge stars die by following the changes in SN 1987A, the nearest supernova that has been seen. These achievements made the Hubble Space Telescope even more important as a foundation for modern astronomy. Its amazing finds about space have captivated people all over the world. With the James Webb Space Telescope, JWST, which was launched after Hubble, new technologies were added and lessons were learned. One example is how we think the world began, which is now explained by the popular Big Bang Theory. The universe began as a very hot and dense center about 13.8 billion years ago. It quickly grew and created matter, energy, and basic cosmic forces. As the universe grew, it cooled, which is what caused atoms, stars, galaxies, and other things we see today to form. The Big Bang Theory also explains the large-scale framework of the universe, the amount of light elements, and the cosmic microwave background radiation. Even though the Big Bang Theory is widely accepted, it had problems and skepticism at the start. Other theories, like the steady-state theory, suggested a universe without a singular beginning, and there were worries about the evidence for the initial singularity, the mechanism of expansion, and observed phenomena. But most of the complaints were taken care of over time. Finding cosmic microwave background radiation in 1965, which fit with predictions of the Big Bang, was a key piece of proof. Progress in telescoping and space missions like COBE and WMAP added to the evidence for the idea. Measurements of the cosmic microwave background radiation were surprisingly close to what scientists thought they would be. Here comes the James Webb Space Telescope, which has high-tech infrared tools that can see through clouds of cosmic dust. The JWST mostly works in the infrared range and sees objects that were made soon after the Big Bang by picking up the universe's oldest and faintest light. Because it can see infrared light, it can study areas where stars are being born, stellar nurseries, and star-forming regions that regular telescopes can't see. Infrared light has longer wavelengths than visible light, so it can pass through cosmic dust clouds and get around a problem with the Hubble Space Telescope. The JWST can see cooler objects that mostly give off infrared light, which makes it perfect for studying things like exoplanets, brown dwarfs, and galaxies far away. As objects in space move farther away, the light waves they send out get stretched, which causes a shift toward longer wavelengths. This is called redshift. The JWST's infrared powers pick up these redshifted signals, collecting light from the early universe and giving us clues about how it formed and changed over time. Infrared light is mostly given off by energetic events like black holes forming or new stars being born, which gives the JWST even more ways to explore. With the telescope, you can look into things that are normally hidden or not visible. The JWST is better than optical telescopes like Hubble because it can pick up infrared energy and is more sensitive. With this ability, it can look farther into space and learn more about the history of the universe. This can show hidden cosmic wonders and give a more complete picture of how the universe has changed over time. The JWST gives us a look into the early stages of how the universe formed. Scientists have recently found something so amazing that it might make them rethink the whole model of the universe. Huge clusters of galaxies at the very edge of what we can see. A few 100 million years after the Big Bang, when the universe was just starting to form, these galaxies were already there. The strange thing is that we don't know how such huge structures came to be so early in the history of the world. We might have to rethink what we think we know about how galaxies formed and changed in the early universe because of this finding. To figure out how the universe came to be, we need to study early galaxies. We can learn more about how galaxies, stars, and planetary systems formed and changed over billions of years with the help of the JWST. In addition, these findings help us learn more about the basic features of the universe, such as its makeup, structure, and the forces that control its growth. The Hubble Space Telescope was very advanced for its time, but it wasn't able to see very far into the past. Its biggest problem was that it couldn't get through cosmic dust and pick up the infrared light that old galaxies gave off. Visible and ultraviolet light views were limited by older telescopes. This made it hard to study the early universe, since cosmic dust and gas absorb or distort these wavelengths. The James Webb Space Telescope is a huge step forward in our ability to study galaxies from the very beginning of the universe. The JWST is different from earlier telescopes because it can look at objects in space that were made just a few 100 million years after the Big Bang. The JWST's infrared sensitivity and advanced imaging skills have revealed many old galaxies, giving us a level of clarity and detail that has never been seen before in our understanding of the early stages of the universe. Early results from JWST observations have caused waves in well-known theories of the universe. The detailed data calls into question some parts of current theories, which is forcing cosmologists to rethink basic ideas that guide our understanding of how the universe formed and evolved. There have been heated arguments in the scientific community about the differences between what has been observed and what theory says should happen. The JWST's observations found more galaxies in the early universe than what previous models had suggested. This suggests that the formation process was more complicated and happened more quickly. Some early galaxies that have been seen seem to be further along in their development than expected, which goes against the idea that they will develop more slowly. Finding an unimaginable number of galaxies questions the way we thought cosmic structures were arranged and distributed, showing a denser and more complicated web than we thought before. These findings bring up interesting questions and new ways to look into things. Early models of how cosmic structures form were thrown into doubt by the existence of massive structures. This led scientists to improve models in search of a better answer. Figuring out how such huge structures came together so quickly after the Big Bang is a puzzle that needs an answer that doesn't go against basic ideas of astronomy. Unexpected differences between what we know about the early world and what we thought it would be like. Models that are based on current ones have also been shown off. These differences could point to physical processes, situations, or cosmic events that haven't been seen before. Scientists have had to reevaluate and improve our models of the universe because of these changes. At this point, all we can say is that more study is needed to figure out how to fit these strange observations into a bigger picture of the universe. First findings can give us exciting glimpses of the universe, but more in-depth studies can sometimes show us differences. For instance, early studies might point to certain features or formations in faraway galaxies that, upon closer inspection, reveal differences in their makeup, structure, or evolutionary paths. Simply put, things that happen in space are very complicated and need to be carefully studied in order for us to fully understand what they are. One example is spectroscopy, a method used to learn about the properties and history of things in space. It includes looking at the light that cosmic objects give off or take in. Spectroscopy looks at the properties of light to get specific information about the chemical makeup, temperature, density, and motion of objects in space. This study helps us figure out where the stars and planets came from, how they changed over time, and what role they play in the big picture of the universe. The JWST has shown many examples of initial observations that were different from later analyses. For example, the first observations of galaxies far away suggested that their chemical makeup was mostly made up of lighter elements like hydrogen and helium, which was in line with what scientists thought would happen. Spectroscopic study with the JWST, on the other hand, revealed interesting changes in the signatures of elements, finding heavier elements or compounds that had not been seen or thought to exist in the early universe. This goes against what most people think we know about the chemicals that made up the early universe and how they formed and spread out across the cosmos. In the same way, early theories about galaxies in the universe were based on observations that showed a fairly uniform pattern of growth and order. But more in-depth studies by the JWST showed a much wider and more complicated range of internal arrangements inside these galaxies. These differences have changed how we think about evolutionary paths, which suggests that the rules that controlled the shape and growth of galaxies in the early universe may be much more complicated than we thought. Aside from that, the JWST has also supported a number of older ideas and observations. For example, the JWST's spectroscopic measurements confirm that hydrogen, helium, carbon, oxygen, and nitrogen are present in cosmic objects, which backs up theoretical forecasts. The results are in line with the lambda cold dark matter model, which says the universe has regular matter, and dark energy, and that it all started with the Big Bang. But because new JWST data calls into question some of this model's predictions, other choices are looked at, like the cold dark matter model, which says that most of the matter in the universe is in the form of dark matter. This invisible matter is not like atoms we know. It doesn't interact with electromagnetic forces, but does pull things together. The model fits with what we know about the microwave background radiation in the universe on a large size, like a galaxy. Smaller scales, on the other hand, present problems because the model's predictions about the internal structure of galaxies and the number of small satellite galaxies around bigger ones are not always accurate. Another idea is the quasi-steady-state cosmology, which says the universe grows and shrinks in a cycle that challenges the idea of the Big Bang singularity. This model is still just a guess because it doesn't fit with other models, and there isn't any direct observational evidence to support the idea that it is repetitive. The mirror universe hypothesis posits that there might be a second, mirror image world going on at the same time as ours. This model suggests that the mirror universe might have its own unique physical rules and mirrored particles, which could help explain some of the biggest mysteries in the universe in a new way. But it doesn't have any real-world proof or experimental data, so it's still mostly just a guess. The digital simulation theory says that the universe we live in might be a very complex computer game. Some people say that our reality could be a highly advanced simulation that is carefully designed to look and feel like the real world. This idea comes from intellectual ideas, and it's hard to show that it's true or false using facts. Lastly, the multiverse theory says that there are many universes, and each one has its own set of physical rules and properties. There are an endless number of universes, and each one has its own constants and maybe even dimensions. It's interesting, but we can't directly see or interact with other worlds, so it's just a guess. It's important to remember that even the lambda cold dark matter model was met with doubt at first. Other cosmological ideas may not be as widely accepted as the lambda cold dark matter model. It's hard to say for sure if these ideas are true or false, but they could be looked at if our current model of the universe fails over time. Many experts say that recent discoveries, while shocking, have not disproved the Big Bang theory. Instead, observations from the James Webb Space Telescope, JWST, have helped us learn more about the past of the universe, which is in line with what the Big Bang predicted. Huge groups of galaxies at the edge of the universe that we can see show that gravitational forces were at work even in the very beginning, which fits with what the Big Bang said would happen. The fact that these huge structures are at the edge of the observable universe means that their light has been traveling for billions of years to reach us. This gives us a look into the past of the universe and backs up the theory's statements about how it will change over time. But these findings also bring up some problems that need to be looked at by scientists in an unbiased way. The JWST has given us new views and let us study the universe's oldest parts. When we look at the universe through the JWST, we see a lot of new questions and interesting prospects. These unknowns question well-established cosmological paradigms, forcing us to rethink what we know about the beginning, development, and basic principles of the universe. In light of these kinds of discoveries, it's important to keep an open mind about changing our stories about the universe. These new findings are just the beginning of the long story of cosmic exploration. They encourage us to keep looking for cosmic truths through more research and new ideas in the field.